Hello everyone, I am Srbuhi Mirzoyan and today I will be presenting my research on heterogeneous GNN for label noise mitigation in biomedical knowledge graphs. The presentation consists of background, methodology, and experimental results. Biomedical knowledge graphs are graph-based representations of biomedical data. They consist of nodes representing biomedical entities such as genes, diseases, connected by edges representing causal interactions, associations, or regulatory effects. One of the common ways to construct biomedical knowledge graphs is the use of scientific knowledge bases, from where triples of biomedical entities and relations are extracted and further used in GNN-based downstream applications. At the same time, with the recent advances in large language models, it is very easy to generate malicious scientific articles that have wrong facts. Moreover, the absence of peer review process on print servers makes them less likely to be examined and thus more vulnerable to being updated with such malicious scientific knowledge. This introduces a critical research problem. How can we assess the reliability of edges in literature-derived biomedical knowledge graphs? In practice, determining edge reliability is even more challenging due to inherent uncertainties and the presence of noisy labels caused by human error, data imperfections, or ambiguity. This figure clearly illustrates the severe performance drop of widely known GNN models for edge classification tasks under increasing levels of edge label noise. Therefore, the aim of this work is to research edge reliability problem under noisy label scenarios in heterogeneous knowledge graphs and develop a noise-robust heterogeneous GNN framework. The core idea of our proposed framework is to combine two mechanisms: a variational information bottleneck to filter out noisy or task-irrelevant edge information, and dynamic edge weighting scheme to downweight the influence of unreliable edges during training. Formally, given a heterogeneous biomedical knowledge graph built from scientific articles, where each edge has a binary label indicating if it's reliable or not, the task is to predict the correct edge label while dealing with varying amounts of asymmetric noise. To efficiently solve the problem, we introduce heterogeneous variational information bottleneck-based weighted graph neural network, which consists of three major components: weighted graph neural network, dynamic edge weighting mechanisms, and edge level variational information bottleneck. The overall process is as follows. First, the GNN outputs source and destination node embeddings, which are then concatenated to form edge embedding. It then enters the edge level VIB module, which consists of encoding, sampling, and decoding to get a concise representation. In parallel, we can see the overall loss function that updates the edge weights and goes as an input to the weighted GNN. To evaluate our framework on a real-world scenario, we constructed a novel knowledge graph using one-year data from PubMed and bioRxiv and used the source information of triples as proxy for reliability, marking edges from PubMed as reliable and from bioRxiv as unreliable. We report the overall and per-edge performance using threshold-independent AUC score. HVIB-WGAT outperforms all other baselines and HVIB enhanced baselines as well, indicating that weighted attention mechanisms perform well in noisy scenarios. Next, we conducted ablation studies, taking out the VIB and dynamic weighting components respectively. Results shows that removing either component results in performance drops. To show the broader impact and generalizability of our framework, we assess it on a public heterogeneous graph, a prime KG, and homogeneous biomedical citation network PubMed for link prediction tasks. In case of prime KG, we can still see the good performance of HVIB WGAT, but in case of PubMed, we can see that graph conf enhanced HVIB performs better. So, to summarize, this research proposes a robust graph neural network framework for edge reliability classification in noisy heterogeneous biomedical knowledge graphs, and the proposed framework proved to be efficient under varying noise scenarios across edge types and graph types. Thank you.